forgot to post the grades on Blackboard, so. Sorry, usually I do. Like, usually is, what I do is I sit next to my computer and all that, but, I didn't.
Well, you got them on before class. That's
Yeah.
You need a beer that night.
Shh. I was doing it at the same time. Optimizing my time.
Is the drinking affect your grading?
Only in a good way. I usually get nicer the more I drink.
Hey, are you buying us beer or something in the class?
Sure.
Okay, thank you. After this hard work.
I mean, it couldn't hurt. Apparently.
It's not bad.
That's
Did you get 100?
I'm expecting all the cheap stuff.
It works just as good as the expensive stuff. I don't care.
Today on the 16th.
No, the only thing I didn't feel really good about was the one that we were talking about with like the Boolean algebra. Yeah, I felt pretty good about it. I was like, well, and the earlier 2 questions, maybe I could say. But I didn't bomb any of the questions. This is just the way.
Well, the 2 point
Thank you.
pretty much all
Yes, sir.
Take the exam today?
Yeah.
Or are you going to take a different class?
So that's kind of.
That's okay. I just didn't know because I don't know if I need to return them. So you have to- Okay, that's all right. Not a big deal. I just needed to know. You're good.
So it's the final take home?
No. No. You're right. Come on, Chris. I mean, I could make it take home, but I could make it much more difficult than the
Well, you could, but you could make it take home and not make it any more difficult.
See, what I was thinking is just make it take home and make it ridiculously impossible. So that way when I grade it, it's just an easy to put a 0 on it for everything.
You should make it really, really difficult and make it 100% from 0 to 10 points. And anything above that.
I kind of like the idea of just giving it to you guys in class.
Just give us all hundreds and we can call it a day.
Oh boy. There seems to be something very ethically and fundamentally wrong with that.
There's a lot.
Definitely a lot wrong with that. I wouldn't feel right doing that. I mean, I think of all the classes I just suffered through. None of my teachers ever gave me a break.
What about the ones you study 20s to?
I didn't know. Professors don't take 20s. You can't label it that.
Yeah.
But you don't take 20.
I think 5s.
Do it simple on Kindle. Like, see, when I had Pink for Calc 2, I actually had a D in the class, but she bumped it up to a B.
How?
That's
I have her right now.
Yeah,
It's my
it
secret.
For Calc 2?
Yeah.
Work really, really hard.
You ever heard of a guy called George Danzig? You never heard of him?
I'm actually doing
So he's a very famous mathematician. So he was doing his PhD, so he came to a class. So the professor wrote something on the exam. So the class, he missed the class. So it was supposed to be his final. So there were three problems. So the professor asked them to do 2, but he did not, since he was not in the class, so he took all 3 problems. So he did the 2 problems really good. The 3rd problem was known to be the most unsolvable problem in mathematics. It took a very long time and he solved it. And he gave it to his professor. His professor was so surprised that he gave him a PhD for that.
Nice.
Look at it, George Danzig. So maybe this take home could be like that.
Maybe. Probably not.
We get an answer, we get a PhD.
Not from here. I could not grant that. Okay guys, so I guess what we'll do today is we'll start recursion and then we'll finish it up next time. You guys may or may not have checked this, but on Blackboard I posted the next Monday I canceled class because of the Thanksgiving holiday. So if you show up here next Monday, good for you. You'll come to an empty classroom or whoever else decided not to check Blackboard. Okay, so if you want to, we can hold class. I don't mind.
Is it Monday or Wednesday? Wednesday we are off. Monday also?
Wednesday we're already off, but Monday I canceled class.
Oh, okay, so we are off the whole week.
Is that a problem? I mean, we can definitely show up.
What's not gonna hurt us?
Oh, I'm
That's the
sorry.
only class I'm on.
How many more sections do we actually have?
2.
too.
Yeah.
Oh, no, I meant-
So I've already checked the schedule, we're good. I wouldn't cancel class if we didn't have the time.
Right, yeah, as long as it's not gonna hurt us.
It's not gonna hurt you guys. I
Are
wouldn't-
we ahead anyway? Oh, no, no, never mind.
We're on
Push back
pace,
to
we are good, so trust me, I wouldn't put you guys in a disposition where we're rushing, okay? All right, so any other questions about canceling class? I didn't think it was a big deal, I didn't think it warranted a 2-minute discussion, but, okay. All right, so basically, guys, when we talk about recurrence relations or recursion, we're basically saying that each iteration thereafter of the sequence is predicated upon the previous one, okay? So, and then essentially we need some initial condition to be able to generate or spawn new iterations in the recurrence relation, okay? For you guys that ever programmed recursion, recursion is a very expensive way to generate iterations, okay? In fact, if you run 100 of them, it can be very costly very quickly. So what we're going to learn is that there are ways to take something that's recursive and write it into something that's just non-recursive, and then you can access the index very easily, okay? That's actually one of the most important things that a computer scientist could ever do, is to get something out of recursive and write it into something that's just linear, and you get the output directly from the input. All right. So one of the first things that we have to do is, if I give you guys some sort of recurrence relation, just be able to write out the iterations of that. Okay? So let's say we have this recurrence relation, a sub n is equal to 3a sub n minus 1 minus 2. And I give you that the initial condition is that a sub 0 is equal to 2. And I ask you guys to list out the first 6 terms of the sequence, okay? The first term's got to be really easy. What's the first term in the sequence?
2.
Yeah, because it's given to you, right guys? So you can't get that one wrong. Well, you could, but that'd be embarrassing. All right? To get the next iteration of the sequence, all you do is you substitute 2 back in for a sub n minus 1. So a sub 1 is going to be equal to 3 times 2 minus 2, which is equal to 4. Okay. Does that make sense to everybody, guys? You just plug in the previous iteration to be able to generate the next iteration. Now, it's okay. If anybody else comes in, just make sure they get one of these for me, please. Thank you, sir. Appreciate it. To be able to generate the next iteration, which we'll call a sub 2. That would be 3 times 4 minus 2. Otherwise known as 10. Okay? And then we just keep going on thereafter for the other 3 times. So a sub 3, 3 times 10 minus 2, that's going to be equal to 28. A sub 4, 3 times 28 minus 2, that's going to be 82. And then finally, the 6th element, 3 times 82 minus 2, that's going to end up being 244. Okay? So that's what a recurrence relation is, guys. I mean, it can't get much easier than that, right? Input, output. Okay? Now, unfortunately, okay, to get to this element, obviously it took a little while to be able to take something like this and to get to that 6th element, okay? Imagine if we were doing that by hand and I asked you guys for the 100th element, okay? We'd be here for a long time writing out each of these iterations, okay? By next time, okay, we might not get to it today, but next time, we can actually take this sequence right here with this initial condition and we can write it so that it's non-recursive, so that it's explicit. Remember we talked about explicit and implicit, and this is recursive. We can write it into the explicit form where we can just stick a number in it right away. Okay, that's what we're ultimately trying to get to. Okay, makes sense, guys? Okay, we could even have these sorts of sequences with more than one recursive term in it. Okay, so we have this recursive sequence b sub k is equal to 2, b sub k minus 2, plus b sub k minus 1. And again, I asked you guys for the first 6 terms of the sequence. The first 2 terms gotta be easy. That would be 2 and negative 2. So b sub 0 is equal to 2. B sub 1 is negative 2. Okay. If I wanted to figure out what b sub 2 was, okay, can somebody substitute and tell me what b sub 2 would look like without giving me what the answer is? But what do I substitute
So
where?
2 times negative 2,
So 2 times,
negative 2.
not negative 2, times 2, right?
Oh, you
Because
have to
wanna
do
go-
with
if
the
you
initials.
notice, it's k minus 2. That means 2 iterations
Oh, okay.
ago. Okay? So 2 iterations before this one would be positive 2.
Okay,
And
good.
that would be plus negative 2.
Good.
Okay, does that make sense, Art? Okay.
Gotcha.
This, guys, the k minus 2 means 2 iterations previous, k minus 1 means 1 iteration previous. That's probably the easiest way to think about it, okay? This will just work out to be a regular old 2. And then we can go ahead and just substitute again, okay? So for b sub 3, or you want to redeem yourself, sir, and tell me what this one looks like?
B sub 3 should be 2 times negative 2 plus 2.
Yes, sir. Which is equal to negative 2. Okay. If we were to compute b sub 4, b sub 4 is going to be equal to what, guys? 2 times 2 plus negative 2, otherwise known as 2. And then, as you guys can see from the pattern that's going on here, you guys can probably guess that b sub 5 is negative 2, but let's just verify that b sub 5 is going to be 2 times negative 2 plus 2, which is indeed negative 2.
Oh, so this is what I call harmonic or something like that?
Not harmonic, good try, all right? It's actually something called an oscillating
Oscillating,
sequence.
that's right.
Not alternating, but it is alternating, but it's also oscillating between two values, okay? So, by the way, guys, both of these are divergent sequences, right? Meaning that they never really reach a specific value. Okay, question, gentlemen? You sure?
They're retired, yeah, no.
Okay,
We're good.
yeah, just don't talk when I'm talking, we'll be good. All right, other questions, guys, I can answer? Okay, so these are our first two instances of being able to work with recursive sequences. Pretty easy, right, guys? We can all do this, okay? One of the things eventually we're going to do is we're going to be able to get to a recursive sequence and be able to verify that they do satisfy. So that I think that's the next thing that we should do, is that if I give you guys something that's an explicit sequence, I want you guys to be able to show me that it satisfies the recursive sequence. Okay? Now eventually what we're going to be able to do is we're going to be able to get to this. Okay? But for right now, we can only verify it. Okay? It's sort of like when you guys learned basic algebra. One of the first things you guys learned was plug the number in and verify that it satisfies. All right? This one, I'm giving you guys the answer, we're just verifying it. Okay? So I give you guys that the answer, or the sequence, is a sub n is equal to 3n plus 1. And I'm giving you guys that the relation that is in question is going to be a sub k is equal to a sub k minus 1 plus 3. Okay. So, this is really the answer to the question that eventually we're going to be asking. Okay? Our job is to verify the answer. So here's how we're
So
going to do this.
the answer is the relation?
What's that?
Which one is the answer, the relation?
The sequence is the answer.
The sequence
okay?
is the-
Because that's non-recursive. Okay?
Okay.
We want something that's not recursive when we can. So what we're basically saying is that these two are the same thing. Okay, they'll produce the same terms. This one's much easier though. Like for instance, if I wanted the 25th term of this guy, I would have to do 25 iterations. If I want the 25th term of this, I just stick 25 in for n. Okay? So this one's much less costly. Okay, so here's how we're going to verify this. All I'm going to do is I'm going to substitute a k in for the n over here. So a sub k is equal to 3k plus 1. Okay? So all I'm doing is I'm just taking whatever the subscript is, and I'm substituting it back in for k. Okay? That's going to be equal to, instead of n, I'm going to plug in a k plus 1. So this is 3 quantity k plus 1 plus 1. Okay. And then, is that a plus 3? Yeah, plus 3 over there. I have a feeling it probably should have been minus 3. Let's do this. Let's change this to minus 3, just to make it work. Sorry about that. So, on your guys, on the sheet, just change this plus to a minus. Just so we can make it work so I can show you. Okay, so I probably made a typo when I was developing this. Okay. If you guys will notice, you can distribute and collect on the right-hand side. So you guys would get 3k plus 1 equals 3k plus 3 plus 1 minus 3. Or in other words, 3k plus 1 equals 3k plus 1. Okay. And that verifies that that sequence satisfies that relation. Okay. And again, guys, it's much, much, much easier to work with this animal, which is just a linear sort of sequence, as opposed to this recursive sequence, okay? So, does that make sense, guys? All you're doing is you're just plugging in a subscript back in for the end. That's all you're doing. And then you're doing some algebra, okay?
Yeah, that's where it's the very beginning I
Okay.
didn't follow.
So, all I did, see this k minus 1?
Yes.
Oh, that's what I did. I'm sorry, guys. All right, so let's do this over. Just erase everything that we just did.
It would be +3 then, wouldn't it?
Right, it would be plus
Right.
3. So I had it right the first time. So I'm just telling everybody to erase everything. Okay, it actually does work as it was. So this was plus 3. Okay, sorry about that. The left-hand side was fine. So all we're going to do is we're going to substitute k back in for n. So that's 3k plus
So
1.
you're making the a sub k equal to the right side of the sequence, except with a k instead of the n.
Correct, right. Because all we're doing is we're saying if this is a sub n, whatever n is, you just plug in here. It's just like a function, okay? Like a one-to-one correspondence. If this was pi, this would be 3 pi plus 1. So over here, since this is a sub k minus 1, this would be 3 quantity k minus 1, okay, plus 1, okay? So that's the sequence with k minus 1 in there, okay? So sorry about that. I thought for some reason it was plus 1 when I did it initially, okay? And then we still have the plus 3 that we're bringing down. Okay. So what I have in brackets, this is a sub k minus 1. This would be the previous term, okay? And this would be the next term, if you would. You guys can clearly see if we distribute and collect, the 3's would cancel out. We'd be left with 3k plus 1, which is what it should have been the first time. So this is 3k minus 3 plus 1 plus 3. 3's cancel out. 3k plus 1 equals 3k plus 1. Okay.
So wherever it's n, we just substitute as k.
That's all it is. It's literally just a linear equation problem. You substitute back in for n just like you would a function. Okay? Think of the subscript as the input back in for n. That's all you have to think of it as. Okay? So does that help, guys? Any questions about that? And I apologize for the sign error the first time. Okay? And again, this is what we're eventually going to get to, but for right now, I'll just give you guys the answer. Okay? We can do the same thing with the next example. So for the next one, we're saying that the answer to the recursive sequence is minus 1 to the n over n factorial. And this is what we're trying to make into something that's not recursive. Okay, so let's go ahead and do that. So the sequence we're given is b sub n is equal to minus 1 to the n divided by n fact. And the relation, this is the same exact thing you guys have on the paper, just so that way I have room for this. B sub k is equal to the opposite of b sub k minus 1 divided by k. So, again, just like a function, we're going to substitute k, and then we're going to substitute k minus 1. When I substitute k back in for n, this just becomes minus 1 to the k divided by k factorial. Okay. So, that makes sense, guys? All we're doing, we're just substituting the k. Okay. On the right-hand side, this is the opposite of minus 1 to the k minus 1. So it's the opposite of minus 1 to the k minus 1 divided by k minus 1 fact divided by k. So once again, guys, all I did was I substituted k minus 1 back in for n. And then we have this denominator of k because that's what was given to us. Okay, so does everybody understand how I substituted there?
Shouldn't that be
Any
k
questions?
factorial all the way at the denominator because it's n factorial, right?
Well, remember, okay. See how it's k minus 1? So I plugged k minus 1 right in here for n. So that's how I got k minus 1 factorial. See how it's k? I just dropped the k down.
Oh, so, okay, gotcha.
Okay? This k is independent of this sequence.
Sequence,
Okay? It
gotcha.
has to be there no matter what.
So if you carry the k minus 1 on the bottom problem, why was it k? Never mind, I thought it was k plus 1. I think I just wrote it down wrong.
Okay, yeah. It's easy to do that, isn't it? Okay, I was a victim of that last time. All right, other questions, guys?
So for everywhere where there's M, we're only using, so if there were any other M, we would always use K minus one.
Yep.
Because that's where it's with the B.
Correct, right. This subscript is basically the input for your function or your sequence. Okay? All right, other questions, guys? All right, now we have to simplify this pretty obviously. So if you guys were to simplify, let's just take a look at the numerator. Okay? How would you guys simplify that if it simplifies at all? Any ideas?
Can you do negative 1 to the k times negative 1 to the 1, like split it up?
Oh, I see what you mean. So like this negative right here, you could think of that as like negative 1 to the first power. And then since you have a negative 1 to the k minus 1, you could use your product rule to be able to add those together. So we would have, and this is the right-hand side, so this would be the same as minus 1 to the k minus 1 plus 1. Okay. Is that what you meant, Donnie? Just shake your head yes and say,
Yeah.
yeah. Because guys, this is just your negative 1. Okay, does that make sense to everybody, guys? That's just a negative 1. And then you're multiplying it by negative 1 to the k minus 1. So that just makes it negative 1 to the k minus 1 plus 1. There's one more negative 1 floating around out there. Okay. What about this best down here? So, Frank?
Just multiply it by the reciprocal.
Yeah, because if you multiply by the reciprocal of that, so this would be k minus 1 fact times the reciprocal of k, which is 1 over k. Okay, right, is that what you meant, sir?
Yes.
With that? Yeah, nice. And hopefully you guys are seeing what's going to happen with this, right? Because obviously in the numerator, this just becomes negative 1 to the k, because the exponents will cancel out and just leave you with k of those. And then we have k minus 1 fact times k. Well guys, what do you know about k times k minus 1 fact?
K fact.
Yeah, that just becomes k factorial, right? So this is every term, or every factor up to k minus 1, and this is the k. So if we wrote it like this, k times k minus 1 fact, that's really the same as just k factorial. And that indeed gives us what we're looking for, the b sub k. Okay, so it does work out nicely for this one. Okay, so just some algebra with this. Hopefully not too difficult for you guys. But does everybody see the trick here with the negative 1? That's really just negative 1 to the first, and then we just added that negative 1 and the positive 1 together. And then this trick right here where you have k minus 1 fact. Okay, so any questions, guys, I can answer about that? Okay, we can even do it if we have a couple iterations back, much like we did with our second example we worked today. So let's take a look at something like that. Bless you. So we have a really basic sequence, okay, which is just 2 plus n. And then we have a not so simple sequence of something we actually almost solved today, 2c sub k minus 1 minus c sub k minus 2. It looks close to what we solved, but it's not exactly. Okay, so we have our c sub n equals 2 plus n, and then we have c sub k equals 2 c sub k minus 1 minus c sub k minus 2. All right. So all we're going to do is we're just going to replace n with k minus 1. Okay, so this is going to be equal to 2 times the sequence when we plug in k minus 1. So that's going to be 2 plus k minus 1. Okay. So does that make sense, guys, as to what c sub k minus 1 looks like? Any questions about that? Okay. And then we have to do the exact same thing with c sub k minus 2. So it's going to be minus 2 plus n, but instead of n, we're going to plug in k minus 2. So it's just a game of substitution. That's all it is. Okay, so let me make sure you guys are all okay with that. And does anyone have any questions about how we substituted? Okay. So now, guys, it's just a basic linear sort of a relationship. I think everybody's able to simplify this fairly nicely. So let's go ahead and simplify it. Okay. In the parentheses, 2 plus k minus 1 just becomes k plus 1. So I get 2 quantity k plus 1. Over here, the 2's cancel out, and that's just left with minus k. We can distribute we get 2k plus 2 minus k, or in other words, that just becomes k plus 2 or 2 plus k. Okay. All right. And of course, we still have to substitute back in here, but that's just 2 plus k anyway. So it looks like it works out rather nicely. Okay. I think one of the most difficult steps is just the first step where you guys substitute. Okay? So just be careful when you're substituting. Okay? Make sure you use your parentheses when you're substituting. In fact, if you want to, you can think of the sequences just like they're functions to make it really easy on yourself. Okay? Like what you guys remember in pre-calc when you're doing function composition. This is essentially what you're doing with this, and it's simplifying. Okay? All right. Questions I can answer about if I give you the sequence that satisfies a recurrence relation, how to verify it. Okay? And like I said, that's pretty easy to do. The hard part is getting to this animal, okay, which we'll eventually do, maybe today, most likely next time. Okay, Don?
Can you tell me how you got the 2 in front of all the first parentheses?
Right here?
Just in case, is that from the,
Yeah, that 2 is from right here.
So anything other than the k plus, the k minus 1, you also put into the...
Right, so what I did was, this k minus 1, I just plugged it in for n.
Yeah.
And I also brought the 2 over, so I have 2 plus, instead of n, k minus 1.
Okay, so the 2 just follows it, like...
Yeah, we just drop it down, okay? Just like function composition, if you're plugging in a function, okay? Other questions, guys? All right, before we can start talking about how do we get to this answer, we have to talk about 2 very common types of sequences, arithmetic and geometric sequences, okay? Both of them are very easy to work with. Some of you guys, or most of you guys have probably worked with them already, all right? There's 2 different ways to write an arithmetic sequence, okay? You can either write an arithmetic sequence in the closed form or the explicit form, where we have this, okay? This is the nice form that we want. Or you could write it in the recursive form, to where you just keep going through and you keep adding a common difference each time, okay? Now, we know that recursive is bad and a closed form is good. Okay, so if we can get to a closed form, that's great, okay? But if not, then we have to rely on the recursive form. All right? The same thing for a geometric sequence. Okay, geometric sequence just means you keep multiplying a number to get to the next one.
Can not all recursive formulas be put into?
Correct. Okay, that's an excellent point. Not every recursive formula has a closed form, if you would.
What's an example of it?
Oh boy, I can come up with literally
that's fine.
yeah. There's many more. It's like have you suffered through Calc 2 yet, Ryan?
I am suffering.
Okay, so you know that not every integral can be evaluated, right?
Correct.
Like I can make up 100 integrals off the top of my head. It's the same way with these, okay? So unfortunately, not every integral can be evaluated, just like these, okay? There's a lot of them that I can make up that don't have closed forms. Okay. All right, so by the way, arithmetic sequence, we just keep adding numbers to get to the next value, okay? So just an example of an arithmetic sequence, I'll just write one up really quickly. Example of arithmetic sequence might be 5, 9, 13, 17, 21, etc. Okay. In fact, I just happened to borrow that one for some reason down there. So, but guys, notice that each time you're increasing by 4. That's an arithmetic sequence where you have a common difference each time. Okay. A geometric sequence, you multiply by a common factor. Okay? It can either be written as recursive or as a closed form. Okay? Again, the closed form is the nice form, the recursive is not so nice. Like for instance, guys, a basic example of a geometric sequence might be something like 1, 3, 9, 27, 81, 243, etc. Okay? Notice that the common ratio, okay, or the common factor to which we multiply each time is by 3. Okay? So that's the difference between arithmetic and geometric. Arithmetic you add, geometric you multiply. Okay, in fact, that might be easier for you guys to remember. All right. All right. So, one of the things I'm going to ask you guys to be able to do, both for homework and also on your final, is I'm going to give you guys a geometric sequence, okay, in the explicit form. What I want you guys to do is to write both the recursive and the closed formula for the sequence, okay? And then I want you guys to find the 10th term in the sequence, okay? And you can either use the recursive method or you can use the closed method, okay? We'll figure out which one's easier in a few moments, okay? So let's go ahead and get to it, okay? So, in fact, I'll leave this formula up here so we can see it. All right, let's go ahead and do recursive first, all right? The first thing we might need to know is we might need to know the common difference, okay? Guys, in this example, what's the common difference? 4, because each of the terms differs by 4, okay? And we might need to know what the initial value of this sequence might be, okay? So, because if you look at the closed form, we need to know an initial value, a sub 1. So guys, what's the initial value of this sequence?
1.
1, right? It's the first term, okay? So does everybody understand what the common difference is, and does everybody understand what the initial value is? Initial value is just the first term, that difference is just your common difference.
So all the initial value starts at like a sub 1, not a sub 0?
It could start at a sub 0, we just have to do a change of base, if you
Okay.
would, okay? Like remember we did a change of variable earlier in the course? We could do a change of variable here if we wanted to. We're not going to, but we could. Okay. All right, so for the recursive formula, so for part A, I know that the next sequence is going to be equal to a sub n minus 1 plus d. Okay, so we're going to say that a sub n is equal to the previous term, a sub n minus 1, which we don't know what it is, plus the common difference, which in this case is 4. And what I could do is I could use that, and I could just go through and get to the next term, and the next term, and the next term, and the next term. Okay, does that make sense, guys? Any questions? Not meant to be difficult. Oh, go ahead, Chris.
Why is it a sub 1 instead of a sub 0 for the initial term?
It's just the way that this is set up. Like I could make it a sub 0, but then I'd have to change this to n. Okay, so just the way that the formula is written, and quite honestly, I like the other way better, but this is the way the textbook presented it, and because I like to stay consistent with the text, if anybody in here ever reads it, I just don't want to deviate from what's in there. Okay, that's the only reason. Okay. All right, for letter B, we're going to go ahead and we're going to get the closed form, okay, or the, so we're going to go ahead and just plug it right in here. So a sub n is going to be equal to a sub 1, which we know to be 1, plus the common difference, which we said was 4, times n minus 1. And then from there, guys, we can distribute and collect. So it looks like that a really nice closed form for this would be a sub n is going to be equal to 4n minus 3. Distribute your 4 and then add 1. Does that make sense to everybody, guys? Not meant to be difficult, okay? I mean, this is basically like algebra level. This isn't even like pre-calculus level stuff, right? You just plug it into the formula, and there you go. Okay. All right. Now, for part C, it says to find the 10th term in the sequence. Okay? Now, there's two ways to do that. Okay? We could use either formula to be able to do it. Guys, which formula would you like to use
B.
for?
B.
The second one, right? Because it's just a direct input. It's like a function, if you will. Okay? So we could say that the 10th term in the sequence, which we'll call a sub 10, is going to be equal to 4 times 10 minus 3. Or in other words, 37. Okay? Just to illustrate, okay, we could go ahead and use Excel and show that the 10th term of the sequence recursively is going to be 37. Okay, so let me just show you guys. So this is 1. That's going to be equal to a sub 1 plus, what was it, 4, I think? And then we could just keep dragging it if we wanted to. Okay, and you'll notice that, hey, the 10th term is 37. Okay, so you could do it recursively. Let me make this a little bit bigger so you guys can see it. All right. That's not a decimal point, by the way. That's just the bars up there. Magic man. Now you say, oh, it just went another way. Nice. All right. But you guys can clearly see that for us to do this by hand would take a long time, right? It's much, much easier to have something that's non-recursive or linear as opposed to having it to be recursive. So any questions about that?
And you said there are two ways. What is this is the easier way. What is the harder way?
One more time?
You said there are two ways you can do it. This is the easier way. What is the harder way?
Well, the harder way is using this.
Oh, okay.
That's what I meant, like
used
just,
Excel for.
right, and that's why I just used Excel, because I didn't want to sit here and do 10 of those.
Okay.
Okay? All right, guys, so let's take a look at another example. We'll try to. So this time we have 5, 0, negative 5, negative 10, negative 15. So let's just go ahead. We probably need to figure out what D is, and we need to figure out what A sub 1 is. Okay, both of those are very easy. Guys, what's D in this case?
Negative 5.
Negative 5, because each of them differs by a negative 5. Nice. And then A sub 1, that's just 5, isn't it, guys? That's obvious to see. So if I was to ask you guys for a recursive sequence for this, okay, what would A sub n be equal to in the recursive form?
A to the n minus 1 minus 5.
Nice. A sub n minus 1 minus 5. Good break. Does that make sense to everybody, guys? It's always A sub n minus 1. Then you just add the common difference, okay? Everybody in class can do that. Now, it's easy to do that, but it's not efficient to do that, okay? What's much more efficient for us is to use the closed form method. So remember our formula, we just take A sub n, or we just take A sub 1, plus the common difference, which is negative 5 times n minus 1. So, is that right with everybody, guys? Any questions about that? All you do is you just take your A sub 1, and you add to it the common difference times n minus 1. We can distribute the negative 5, so I believe we get minus 5n plus 10 to be the closed form for our sequence. Okay.
Can we, take out, the 5,
Yeah, if you want to go ahead and factor out a 5 or a negative 5, you certainly can, okay? I don't necessarily know if it helps or hurts any, but it just is what it is, okay? But you're not wrong to do that, Donnie. Let's say that, okay? All right, does that make sense to everybody, guys? If I wanted to find the 10th term of the sequence, just like I did in the previous problem, I could either do it recursively, or I could just stick 10 back in for n. So that would be A sub 10 is equal to negative 5 times 10 plus 10. And I think we end up with a negative 40. Is that correct, guys? Sure, why not? Okay. Once again, I'll illustrate using Excel that we could get it using the recursive. Okay. So we said the first term was 5. And this is equal to B sub 1 minus 5. Okay, and then we'll just drag it down to the 10th term, and there we go, we get negative 40. Okay? Either way we want to do it, it works. But again, and I keep saying it over and over and over again, just because it's kind of important, if you guys can do it linearly, much more efficient. Questions I can answer, guys. Okay, that's our arithmetic sequences. Let's take a look at a couple geometric sequences. Okay, so we clearly see that for this sequence, 5, 15, 45, 135, we're not adding a number to get to the next term, right? I mean, we could add 10, but then all of a sudden we're adding 30, and then we're all of a sudden adding 90. Okay, so 10, 30, 90. That might be difficult for us to generate some sort of pattern for. Okay?
Go up just a little bit.
Oh, what you need? Oh, just go back up a little bit more.
Yeah, that.
Is that good? Okay. So for this guy, guys, we're using the geometric relationship, okay? And you guys have your formula for the geometric relationship. So once again, we need not D this time, but we need R, and then we need an initial value. Okay. So guys, clearly in this example, what's R going to be? 3, right? The common ratio is 3. Each successive term, we're multiplying, or each successive iteration, we're multiplying by 3. And then clearly the initial value is 5. Okay, we're hopefully clear. So if I wanted to get the recursive definition for this, A sub n, okay, we look back now not at our definition for arithmetic, but now geometric. Okay, let me scroll back up to that just to make sure we're okay with this. Okay, and all you do is you take the initial value and multiply it by r to the n minus 1. Okay. So, or for the recursive, it's just r times a sub n minus 1. All right, so for this one, it would be 3a sub n minus 1. So, does that make sense to everybody, guys? All we're doing is we're just taking the common ratio, multiplying it by the previous iteration, and that'll give us the next iteration. For letter B, okay, now this is the one that's more important to us, especially if we want the 10th term in the sequence, okay? That's going to be equal to, what do we say, the initial value, which was 5, times the common ratio, which is 3 to the n minus 1 power. Okay. Does that make sense to everybody, guys? Any questions about how we substitute those? Okay, it's not difficult, it just is what it is. Now, of course, what we'd like to do is we'd like to be able to verify that if I was to substitute 10 back in, okay, that I get the same thing both recursively and explicitly for this, okay? So this is what we definitely want to have a calculator for, unless we know what 3 to the 9th power is times 5 off the top of our head. So a sub 10 is going to be 5 times 3 to the 10 minus 1, okay? Or in other words, 5 times 3 to the 9th. And I don't even know if your calculator will give you a number for this that's not in scientific notation. If it does, let me know. If not,
98415.
was it
98415.
98415? Okay, that's not as ugly as I thought.
Yeah,
Why did I think it was going to be really ugly?
That's 3 to the power 9. That's not that much.
Yeah, it does. It really does, yeah. I guess it's not as bad as okay. Alright. Now, let's see whether or not this actually works. If it actually does give us the iteration that we need. So, we'll do it recursively. Okay, so we'll start out with, I think our initial value was 5, right guys?
Yeah.
And then to get to the next term, we multiply by 3. So it's c sub 1 times 3. Okay, and let's just drag it down to the 10th term. 98415. That's what we got, right guys?
Yes.
Yeah. Nice, okay. So now we can verify that it works, okay? So that's pretty cool that we can now write it both recursively as well as closed form, okay? So we know that this is the answer, unless we got exceptionally lucky, which we know we're not. Okay, all right, any questions guys about that? Okay, last one that we have here, we have a little bit of fraction stuff going on, so it might be a little bit more difficult for us to find R, but hopefully not. So, if I was to ask you guys in this specific sequence what R would be, anybody think you might know? 2/3, right guys? And isn't it obvious that if you just pick, let's say you pick 8/3 and 16/9, to go from 8 to 16 you multiply by 2, to go from 3 to 9 you multiply by 3. It doesn't matter which two terms you pick, they have to have the common ratio, okay? So that would be 2/3, and then clearly initial value of a sub 1 is 4. So, for the recursive version of this, okay, recursive version is going to be what, guys?
2/3, then a sub n minus 1.
Yeah, 2/3 times the previous iteration. Okay. Really easy, right, guys? Not a big deal. Okay. If we wanted, though, to be able to write the closed form of this, that might be a bigger deal. Okay, so we're just going to go ahead and take the initial value, which is 4, and write that as what? 2/3 to the n minus 1, right guys? We could simplify that, believe it or not. Okay, you guys might not want to simplify it, but we could express it in a different way. Okay, let me illustrate how. Okay. By the way, if you left it like this, I'm okay with it. Yeah, this is okay with me. This is part B, by the way. Okay. But another way you guys, in fact, let me do it over here so I can show you guys. But if we have 4 times 2/3 to the n minus 1, and I wanted to write this in a different manner, okay? Couldn't I write the 4 as 2 squared, okay, because that's what 4 is. And couldn't I write this quantity as 2 to the n minus 1 over 3 to the n minus 1, right guys? And now, don't I have a couple base 2's right here that I could combine into a singular base? So, if I was to combine these, Okay, what would that combine into? 2 to 1
n
power,
plus 1.
n plus 1, okay? Because all we would do is just take this 2 and the negative 1 and we combine it, okay? So another way that we could write this is 2 to the n plus 1 divided by 3 to the n minus 1,
That's way
if we wanted to.
That's way uglier.
I don't know, not necessarily, because now you don't have a coefficient to work with. Now you have 2 bases to work with. I don't know if it's uglier or better or not. You would probably see this version if you were looking at the back of the book answer, believe it or not, because they like to have one common base, okay? It's just, it really is easier to work with a singular common base, okay, whether you guys like it or not. All right, now of course what we want to do is we want to make sure that this works out, okay? So let's go ahead, let's find the 10th term in the sequence, and then let's go ahead and see if Excel likes that using the recursive measure, okay? So for part C, if we wanted to find a sub 10, okay, that would be 4 times 2/3 to the 10 minus 1, or in other words, 4 times 2/3 to the 9. And I don't know if that's going to give you guys a nice fraction or not, if you use the math enter or not, but did anybody get a nice fraction out of this, or did it just keep it into the, it just put it in decimals? Okay. Greg, what'd you get, sir?
1040, or .1040.
0.1040.
And if you want to do the last one, it would round up to 5.
Okay, that's fine. As long as we get that, I mean, it's pretty obvious that we'd be correct, okay? Excel's obviously only going to give us the decimal answer, so it doesn't hurt my
I did get a
feelings.
fraction though.
You got a fraction?
Yeah, 2048
Uh-huh.
divided by 19683.
Do you have an 89?
There's a 3 after the.
Oh, okay, what is it?
After the 8 in the denominator.
Oh, okay, there's a 3 there. I'm sorry.
Well, you can convert it back and forth, right? That's the thing, so
it doesn't
each calculator will give you a different.
Yeah, it doesn't really matter, quite honestly, you're right.
Actually, what I did was I expanded 2 to the power 9, then multiplied by 4,
Oh, okay,
and then
yeah.
3 to the power 9.
Okay, so we had, the initial value was what for this, guys? 4? And then we're going to say that that's going to be d sub 1 times 2/3, right, guys? Okay, so let's hope for our 10th term we get 1040. 0.1040. Nice. And then you said it rounded to 5, correct? Yeah, that looks like it's going to work out nicely. So again, just illustrating that we get the same answers regardless, okay? I think it's pretty neat that we can write the same sequence in 2 different manners, okay? All right. Guys, any questions about being able to write either an arithmetic or a geometric sequence into a closed form or into a recursive form? All right, guys. So, like we've been saying, okay, this is what we're kind of leading up to. What we'd like to do is, if we have something that's recursive, we'd like to be able to write it closed, okay? We can obviously see that closed is much, much, much more efficient than the recursive sequence, okay? So here's how we're going to do this. We're going to use something called the method of iteration, okay? I can't remember. Somebody said that they took differentials already, so, Donnie, and do you remember anything about the series solutions? No, that's okay, I won't remind you. When you guys are taking differentials, you actually use this to be able to get a closed form of a series, okay? So this is something that some of you guys, in fact, have you guys gotten to Taylor and Maclaurin series yet in Calc 2 for those guys that are taking it? Have you guys gotten to the problems where you actually have to go through and just keep iterating it to find a closed form yet, or not yet? Okay. Because there are ways to be able to write them in closed form and you just kind of have to guess it, okay? Maybe your teacher might not even make you do it, okay? I always make my students do it, but regardless. So anyway, what we're going to do is we're just going to keep writing out the terms of the recursive relationship, and then hopefully what we can do is we can be able to verify what, some sort of closed form for this, okay? So the first couple are pretty easy, and then they start getting really difficult after that, okay? So we might only do like maybe the first 2 or 3 today, and then next time we'll finish up the rest of these, all right? So let's start off with one that's pretty easy, okay? So we have this recursive relationship. A sub k equals k times a sub k minus 1, a sub 0 is 1, and k is bigger than or equal to 1, okay? So let's just start writing out the iterations for this. All right, so for the first one, I don't know what's going on here, I don't like it though. There we go. Be gone. So the initial value, no, not gone. That's okay, we'll just do it on the whiteboard. You guys don't have this electronic problem on your papers. Yeah, this looks like it's gonna be fairly ugly, but it's actually gonna work out really nicely. Okay, so we said a sub 0 is equal to 1. Right. If I asked you what a sub 1 is, in other words, what's the next iteration in this sequence, okay? Can somebody tell me what that would look like?
Yeah, that should be like k is 1, right?
Yep, k is 1 because
So
that's the
one
subscript, so 1 times
times
1,
one, yeah.
right guys? And by multivariable calculus methods, 1 times 1 is 1. Okay, well that's nice, okay? Now, what about a sub 2?
2 times 1.
Okay,
Two,
or
1
wouldn't
times
that
2.
be 2 times 1 times 1, right guys?
Yeah.
Just because it's the same thing as the previous iteration, okay? So what I like to do is I like to use the previous iterations to maybe get a better sense as to what's going on with this. If you did 2 times 1, you might be able to see the answer, but I think this might give you a clearer picture as to how we're going to progress with this. Okay? Now clearly, 2 times 1 times 1 is just 2. So it's not looking like it's doing too much with this. Okay? A sub 3. Okay? A sub 3 is going to be what, guys?
2 times,
2 times 1 times
3 times 2 times 1 times 1, right guys?
Mhm.
So all I'm doing is I'm just taking the previous iteration and I'm just sticking that back in. Okay? Does that make sense, guys? That's how a computer would do it, right? Computer doesn't remember the answer, it remembers the elongated form. Okay? So a computer doesn't necessarily do the computations each time until it gets to the end. That's why recursion is extremely expensive, because sometimes the computer doesn't process it all the time. Okay?
Depends on how
Yeah, because if you guys look at the next term, A4, wouldn't that be 4
times 6 times 1?
times 3 times 2 times 1 times 1? Which would be equal to 24. And guys, what a lot of you have already noticed is that, okay, well the next one's going to be 5 times 4 times 3 times 2 times 1 times 1. That's the definition of factorial, isn't it, guys? If you don't believe me, just keep doing it. Okay, a sub 5 would be equal to 5. Now I'm running out of, I guess, differentiating squigglies, so what I'm going to do is I'm going to start with the parenthesis again. 2 times 1 times 1. Which is equal to 120. Now, if you guys, let's say for some reason you guys just had 1, 1, 2, 6, 24, and 120, okay? How many of you guys would have recognized that that's the pattern of factorials? Maybe a few of you guys, right? So some of you guys know like the next one's going to be what, 720, and then 50, 40, and then after that. But I bet you not a lot of you guys know like your factorials up till 10, okay? But I bet you everybody can clearly see that this is just going to be a factorial, right? So if I was to guess a closed form for this, which let's call that a sub n, that would just be n factorial. Okay? And that's much easier to work with. Okay? So what we did, guys, was we took something that was recursive, this a sub k times a sub k minus 1. And then all we did was we just used the method of iteration. And you guys see what the method of iteration is? You're just plugging previous instances back in. And we're not computing, we're just keeping it into the elongated form, okay? A lot of times that'll work out nicely. Sometimes it's just easier to compute. Okay? Questions I can answer, guys? Okay, so let's take a look at the next example. Okay? Again, we're going to use method of iteration, not too difficult. So we have that b sub k is equal to b sub k minus 1 divided by 1 plus b sub k minus 1. Okay. And then we have that b sub 0 is equal to 1, our initial value. All right. Now this one looks like it's really ugly, Believe it or not, guys, this one's a little bit easier than the previous, because everybody's going to be able to see what happens this time. Okay, so we know b sub 0 is 1, right, guys? Everybody knows this. So b sub 0 is 1. What would b sub 1 be equal to, guys? 1 over 2, or 1 over 1 plus 1, right, guys? So I like both of the answers. 1 over 1 plus 1, or in other words, 1/2. Okay? So that's not so bad. B sub 2. There's two ways we can write b sub 2, right, guys? Let's say for some reason I use the previous iteration. Okay? What would b sub 2 look like using the previous iteration?
Half divided.
Well, 1 over 1 plus 1, right? 1 plus 1 over 1 plus 1, right? That's how a computer does it. Computer doesn't have to think about it, it just does it. Okay? Now, Art, what you were saying is 1/2 over 3/2, right?
Yeah.
That's the way we compute it. Okay? So this would end up being 1/2 over 3/2 by computation. And guys, what do we know about 1/2 over 3/2? 1/3, right? The 2's would cancel out because they're both in denominators. So this is just 1/3. Okay, that's not so bad.
Oh, so this whole thing adds up to 2, right? Like if you add the 2 into infinite series or something like that? This is the part of the Ramanujan series, right?
No, it doesn't add up to 2,
Or
but it will converge to a
to
value.
1, right? Or something.
Not 1, okay? It will converge to a value, we just don't know what the value is yet,
Okay.
okay? We can find it, okay? All right, so b sub 3. All right, now this one you're not going to like too much. That's okay. This would be equal to 1 over 1 plus 1 divided by 1 plus 1 over 1 plus 1 divided by 1 plus 1 over 1 plus 1 divided by 1 plus 1 over 1 plus 1. Okay? That's how a computer would remember b sub 3. Okay? Computer's not going to go through and it's not going to say that it's 1/3. It's just going to use the previous instance, okay? Now, of course, guys, we can go through and do this very easily, right? Because we already know that it's 1/3 from the previous. So we know that the numerator is 1/3. Okay. The denominator is just going to be 1 plus 1/3. Or in other words, guys, what's the denominator?
4/3.
4/3, right? And if we were to simplify that, guys, what does that work out to be? 1/4. Now we're seeing a pattern, aren't we, guys? I bet you guys can guess the next term and the next term and the next term, right?
1/8.
No, not 1/8.
1/10.
1/5, right? Because notice what's happening, the denominators are increasing by 1 each time, right?
Okay.
It's not a geometric, it's an arithmetic type of series, okay? So, let's say for some reason I was to ask you guys for some sort of closed form for this. Okay, so, let's say and I wanted to know what b sub n was equal to. Okay, anybody have a guess as to what b sub n is, John?
1 over n plus 1.
1 over n plus 1, okay? John, provided that n starts at what number?
Let's start at 0.
Yes, sir, excellent, because if you plug 0 in, then you get 1, which is the first number.
Or you start at -1.
If you start, let's say you shifted the index, then you would just say -1 plus 2 would get you to that, okay? So you could shift the index, huh?
So it says there we're starting k is greater than or equal to 1, why is it not 0? Because 0 will also give you the first.
Right, for this one, well, what we're doing is we're saying that we already know the first term. So we don't need to necessarily know what b sub 0 is, so that's why we started 0.
Oh,
It has to be given to you, okay? So in this case, what we're going to say is that n is an integer, n bigger than or equal to 0, okay? We probably should have done that for the previous problem. Let's go ahead and do that. We should probably give ourselves some initial values. To make the previous problem work, what should the domain be for this guy? Well, obviously the domain's integers. Yeah, we should start at 0, shouldn't we, guys? Because let's think about plugging 0 factorial in. 0 factorial gives you 1. 1 factorial gives you 1. 2 factorial gives you 2. So we would just say n bigger than or equal to 0. Okay? In fact, let's make that part of the solution. Because for a sequence, we really should have some domain, and we should have some initial value. If we don't have those, then unfortunately this problem doesn't go anywhere. Okay. Questions I can answer about that, guys? Okay. So let's do one more of these, and then we'll be done for today. So I have c sub k equals c sub k minus 1 plus k squared. Now we're saying that case, it should be,
Yeah,
I'm
should
sorry,
be a C sub.
this should be c sub 1 equals 1. So typo, so let me scratch that out, so we don't do that. I guess we're not doing anything. It's not going to like any of that. Oh, there we go. So that's c sub 1 equals 1. Okay. So, c sub 1 is going to be equal to 1. So, we already know what c sub 1 is, right guys? C sub 1 is equal to 1. C sub 2. If I was to ask you what c sub 2 is, what would you guys tell me?
1 plus 1 square.
1 plus
Sorry, 2
2
square.
squared. Good. Okay. Which is 5.
Five.
I mean, that's nice. What about c sub 3?
5 plus 3 square.
Okay,
One
5 plus 3 squared, or
1 plus 2 squared plus
3 squared. Okay. Or 5 plus 9, which is 14. Okay. So, does that make sense, guys, so far? All right. C sub 4.
So 1 plus 2 square plus 3 square plus 4 square.
So 1 plus 2 square plus 3 square plus 4 square. Okay. So guys, does everybody see that all we're doing is we're taking the previous iteration. That's going to be the c sub k minus 1. And then we're just adding the next square. Okay. That's going to work out to be 30. Although that really doesn't help us too much. But I bet you guys can figure out the pattern for C5, C6, C7, right? Like for instance, if I asked you what C5 was, C5 is what?
1 plus 2 square.
And then C sub 6 would be equal to 1 plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, right guys? So in other words, guys, doesn't this recursive iteration sequence just keep adding the next perfect square each time? Okay? So, if I was to guess a closed form for C sub n, okay, what I might guess is I might guess something like n, 2n plus 1, n plus 1 divided by 6, right guys? What? You guys knew this. We proved this already. Exam 2. We can prove this by using mathematical induction, right? Very easy, right? Didn't we take part of the course? In fact, we took a month of our lives to say that if I was to keep adding the nth term, then I would get something that looks like this, okay? Now the question is, well, how do you know that, right? Well, we proved it by induction. If only there was a list of nice closed form summations that you have. Oh, what a coincidence. I have a list of nice closed form summations that we should know, okay? And a lot of these we did prove already, okay? So let me get these out to you guys. Okay. Yeah, and you guys probably wouldn't know that off the top of your heads, okay? I only know it because I have nothing better to do with my life than memorize closed forms of special summations. Yeah, that's it.
You realize it's a movie, right?
Yeah, big bucks, my guys.
We don't believe you, we already know on your free time you just drink.
Oh, yeah. Free time. I'll wait till everybody gets a copy of this, by the way, so, because I want to make sure you guys understand how this works. Okay.
Thank you.
Thanks, Mark. Thanks, Mark. Okay. Guys, take a look at maybe the third or fourth one down. Okay. I want you to notice that 1 square plus 2 square plus 3 square plus 4 square up to n square is equal to n plus 1, 2n plus 1 over 6. I just wrote the formula differently. It's the same thing, right guys? So, now, we could prove this by induction, but we've already proved it. In fact, couldn't we prove any of these by mathematical induction? In fact, a lot of them you did, okay? Like for instance, the first one we did for an assignment, the second one we did for an assignment, this guy was on the exam review, this I think was the actual exam question, or actually no, I think the fourth one was the exam question, or fifth one. This one I'm not touching, the end of the fourth. But a lot of these guys are ones that we either did for homework, or we did in class, or we did it on a review or something like that. So you guys have proven these, okay? It's just up to us to recognize these, okay? And that's where this becomes difficult, because if you didn't recognize that this is from the special forms of the summation sheet, okay, so let's write that. So that's from the special forms of summation sheet, okay? Which you guys are welcome to use for the final, provided that you guys don't write anything on it, okay? It might be very difficult to take this recursive relationship and write it into this relationship, okay? So does that make sense, guys, as to maybe why? Like, remember early in the course, it's like, well, when would I ever use mathematical induction? Well, this is an application of mathematical induction, where we can take these recursive sequences and write them into closed form, proving these formulas, okay? So it's kind of neat how stuff builds upon itself in this course, okay? Questions I can answer about this, guys? All right, now, it doesn't always work out this cleanly, okay? Sometimes we have to do some algebra at the end to manipulate, okay? And that's what we're going to take a look at when we come back after break, okay? All right, so we'll stop here for today. All right, yes, sir?
Where does n start in this?
Oh, that's an excellent question, because if that doesn't work, then we're done with this, okay? So we need the first term to end up being a 1. So I would suspect that n should start at 1 for this, okay? So we're going to say n is an integer. Thanks, John. N bigger than or equal to 1, okay? And by the way, guys, if you don't believe me, just go through and just start trying to figure out for like maybe plug a 3 or a 4 or 5 or something like that in, and you'll see it works out nicely. Okay. All right. Any other questions, guys, I can answer? Okay. So I do have your guys' assignments, and I do have the exams graded. I posted the exam grades on Blackboard. I can't give the exams back yet because I had one student that had a documented reason as to why they couldn't take it, aka jury duty. There's nothing you can do about that when the country calls. So I will give back the assignments, obviously. I can't give back the examinations, all right? But you guys know your grades on Blackboard, all right? And if anybody wants to look at it, I don't mind if you guys come up and look. Okay, thank you, sir. All right, so I'll give you guys back your assignments, and then if you guys don't have any questions for me, then you guys can leave after you get your assignment.